In this video, I am going to get as close as I am going to go throughout the entire course of offering a definition of life. As we discussed before, life is a notoriously difficult concept to provide a thorough definition of. Very often, biology textbooks will list a certain number of criteria, and they will say if you see a thing that satisfies these criteria, that thing could be considered alive. But at the same time, those textbooks also admit that life is incredibly difficult to define in a very thorough manner, and ecologists, biologists are constantly discovering new plants and fungi and animals and bacteria that seem to violate some of those criteria. So there is no good universally accepted definition among biologists of what is a living thing as opposed to a non-living thing. The definition that I'm going to offer in an attempt to define what is a living thing here was popularized by the physicist Erwin Schrödinger. Erwin Schrödinger was one of the founding fathers of quantum mechanics in the early 20th century, and this definition of life concerns the notion of entropy. Entropy is a concept from statistical mechanics. Statistical mechanics is the underlying basis for thermal physics. So thermal physics, the study of temperature, pressure, heat flow, states of matter. Statistical mechanics is the basis for the study of thermal physics. Entropy is often described as the amount or a measure of disorder within a system. So to motivate the notion of entropy, let's look at a game, The Settlers of Catan, where we roll some dice. Now, each turn, a person will roll two six-sided dice, and if you are built next to the number that is rolled on those two dice, then you get to collect a resource from that tile. So, for example, if two six-sided dice are rolled and an 8 comes up, the blue player would get to collect one of this resource because the blue player is built next to the 8 tile. If on the next turn a 9 is rolled on two dice, then the green player and the red player are both built next to the number 9, so both the green and the red player would collect one of this other type of resource. Now, as a thought experiment, you could ask, say you want to build, would you be rather build next to the 8, or would it be more advantageous for you to build next to an 11? Well, you could think about it and you could say, which is more likely to occur when I roll two dice? Is it more likely for me to roll an 8, or is it more likely to have an 11 be rolled? One way you could look at this quantitatively is to list out all the different possible combinations of rolling two dice. So if I roll two dice, there are 36 possible combinations. I might roll a 1 and a 1, that would give me a 2. I might roll a 2 and a 1, or a 1 and a 2, that would give me 3. There are 3 combinations that give me a 4, 3, 1, 1, 3, or 2, 2. And I could list out how many different combinations of rolling two dice will give me an 8 versus how many different combinations of rolling two dice give me an 11. So if I look at this, there are 5 possible combinations when I roll two dice that give me an 8. There are 2 possible combinations of rolling two dice that give me an 11. So it would be more advantageous to build next to an 8 rather than an 11. Now, this is not a guarantee that an 8 will be rolled more. There is a possibility because we are rolling two dice. This is random chance. But we're improving our odds of collecting resources by building next to the 8 versus building next to the 11. So rolling two dice and getting an 8 is the more common outcome than rolling two dice and getting an 11. Now, what if instead of two dice, we roll a lot more dice? What if we roll 1,000 six-sided dice? There are a lot more possible different numbers that might come up. There are a lot more different outcomes that could also come up. So with two dice, there are 36 possible outcomes and 11 different numbers that might get rolled. With 1,000 dice, there are many, many more numbers and possible arrangements of dice to give those numbers. Now, there is no physical law forbidding a 1,000 or a 6,000 might be rolled when you roll 1,000 six-sided dice, but rolling 1,000 is incredibly unlikely because you would just have to have every dice that you roll happen to fall on the number 1. And that, again, is not forbidden, it's just incredibly unlikely. A much more likely number would be something around 3,500. Now, each time you roll 1,000 dice, you probably won't roll a 3,500. You'll probably roll more or less than that. But the number you roll, the total number of all the dice added up, will probably be somewhere around 3,500, within a couple hundred plus or minus of that number. So the reason for this is there are more possible combinations of six-sided dice that give 3,500. There's only one combination of six-sided dice that give 1,000 or 6,000. Entropy, as we said, could be thought as a measure of the amount of disorder in a system. And take a moment to notice how general this description is. I'm talking about the measure of disorder. Well, I'm not really defining what disorder is. I have a notion of what order is versus disorder. Everything is nice and neat and stacked and put in its place versus everything is thrown around randomly all over. I'm also not really defining what do I mean by the system. Is the system a chamber of gas particles, or is the system a bedroom where you have your clothes and your books and your computer and whatever else? Could the system be the Earth or the universe or something else? One way to phrase the second law of thermodynamics is that the amount of disorder in a closed system will tend to increase as time moves forward. So, what do we mean by this? One way you could visualize this concept is to let's say we have a chamber of gas. So, in this chamber of gas, there are two types of particles, red particles and green particles. Now, if the gas particles are all just flying around, moving, bouncing off each other, they're moving essentially all in random directions. If I begin by having all the red particles on the left side of the chamber and all the green particles on the right side of the chamber, the gas particles are moving around, and then I begin watching how will that chamber evolve. As time moves on, the green particles will diffuse towards the left-hand side, and the red particles will diffuse towards the right-hand side. So if this is my initial state where I have the color of the particles separated, as time moves on, the particles will tend to diffuse and spread evenly and mix in with each other. Now, there is no physical law preventing this disordered state to evolve into this ordered state. In other words, all these gas particles are moving around and bouncing every which way. I'll just say, without counting, it looks like we have 25 red and 25 green particles. So if every particle is moving around in a random direction, they all collide with the walls of the chamber, they collide with other gas particles, they might spontaneously just happen to be moving perfectly, so all the red particles end up on the left side and all the green particles end up on the right side for a moment. But that is just very highly unlikely. That would be like rolling a large number of dice and getting 6,000 or 1,000 or something else. It's not forbidden, it's just unlikely. And as we increase the number of particles in a chamber, we are going to get even more and more unlikely to move from a disordered state to an ordered state. And by what do I mean by a large number of particles? I'm talking Avogadro's number of particles. So in the dice example, if you roll 1,000 dice and think about how many rolls would it take for me to get 6,000 when I roll 6,000 dice? Well, what if you're rolling this many dice? That would be even more and more unlikely. And it's so unlikely, we could say for all intents and purposes, it just straight up is not going to happen. If you were to roll dice 1 second for the entire age of the universe and you had this many of dice, you would need to roll dice many, many times the age of the universe if you wanted to get all your numbers as sixes. Here's another example of entropy at play. So here we have something is burning and it is releasing smoke particles. The smoke particles initially are all rising up in the same direction at the same speed, so we have a very low entropy, or in other words, a very highly ordered flow of the smoke. However, later on, as the smoke particles rise higher and higher, these smoke particles become turbulent and their motion is much more random. So we went from a very highly ordered state where we have a laminar flow of the smoke to a very disordered state where we have a very turbulent motion of our smoke particles. Now, if you watch this, whether it be in this picture or you watch something burning and you watch the smoke rising up, you might notice something interesting occur in this highly turbulent region. Occasionally, you might see vortices appear. So a vortex is a spiral motion of the smoke particles. And even though we have a really high turbulent motion of all the smoke particles and a very highly disordered region way up here, the vortices are actually ordered structures. They're a region where the smoke particles are all, again, moving in a fairly uniform pattern in a very similar ordered manner. So occasionally we might see a highly ordered motion of these smoke particles spontaneously appear from a highly disordered state of the motion of smoke particles. What's happening here? Well, it looks like we're temporarily breaking the second law of thermodynamics. When these vortices are created, it looks like we're going from a very turbulent, high entropy state to a low entropy state where we have some motion of the smoke particles that's very ordered. But what's really happening here is that it is true. Locally, within the vortex, you do have a lower entropy than what you previously had. You did form structure out of chaos. So locally, the smoke particles' entropy has decreased. However, entropy increases globally and when we talk about the increase of entropy, we need to talk about the increase in disorder of everything. So within the region where this vortex is located, you did go from disorder to order. But we need to consider the entirety of this smoke. And even though we had an increase in order here locally, globally, if you take all the smoke particles into account, the total amount of entropy is still going to increase. So the slight decrease in entropy, the slight decrease in disorder around the vortex is going to be more than compensated by the increase in disorder of all the smoke particles taken as a whole. This phenomena is also realized in nature. So here's a picture of Giant's Causeway from Northern Ireland. And it looks like we have a very highly ordered state of some rocks. So all the rocks seem to be in a really interesting pattern. And it is true that locally these rocks are arranged in certain patterns. You have the structures within these rocks all seem to fit together really nicely. They're in nice geometric shapes. So I could see these rocks and say locally, these rocks seem to be in a very low entropy state. But in order to form a configuration of rocks like this, the total entropy of the entire Earth must increase. And so the amount of disorder around the region where these rocks are formed was decreased, but the total amount of disorder within the entire Earth has increased to compensate for the decrease in disorder there. So how does this connect to life? Living things are highly ordered systems. Even though we don't have a good definition of what is life, it does seem that life is going to be a highly ordered system. We are going to take in food, which are very highly ordered molecules. We'll break those molecules down into simpler components. We'll release energy in the process. We'll expel the molecules that we reform and get rid of and don't need as waste. In doing this, we are going to generate heat. And thermal radiation is a very high entropy state. So, as a result of existing, the entropy of the environment surrounding a living organism will tend to increase. Now, from this point of view, we could think of life as an entity that is continuously decreasing its internal entropy at the expense of increasing the entropy of its surrounding environment. So basically, a living thing is a highly ordered system, and it wants to remain a highly ordered system. In order to remain a highly ordered system, it must take in energy from its environment and increase the entropy of its environment, increase the amount of disorder within its surrounding environment. So a living thing could be thought of as something that actively opposes reaching thermal equilibrium. So watch the video, The Physics of Life by PBS Spacetime, and then I'll see you in the video right after that.